This is the last part of section 6.7, and we'll be talking here about the application of integration to fluid force and pressure. So what we're looking with is the force that is exerted on some kind of a surface by a body of, we'll use water, but it could really be any fluid. First of all, pressure. The pressure on the surface is defined as the force per unit area. So common units would be like how many newtons per square meter. That's force per area unit. Or in the American system, pounds per square inch, often abbreviated PSI, or pounds per square foot are common units. All right, first of all, we have a relationship between pressure and depth. In a fluid that's standing still, the pressure at depth h is the fluid's weight density W times the height h. Or, keep in mind, if we don't know the weight density and we do know the mass density, we can always say the weight density is the mass density times the acceleration of gravity. Just a reminder, the weight density for water is 62.4, and that's in pounds per cubic foot. All right, so we're going to submerge a surface in liquid, and we want to know the total force that's exerted on that surface, that plate, due to the pressure of the water. This is known as the hydrostatic force, or sometimes just the fluid force. And here's how we calculate it. For a surface with area A that is submerged at a constant depth, h, the hydrostatic force is the pressure times the area. Pressure, note, is WH, so I could write it as WHA, or if I don't know W but I know rho instead, I could do rho G times HA. So let's take a look at a few examples. In example 1, we have a flat-bottomed rectangular swimming pool, 8 meters wide and 12 meters long. It's filled with water to a depth of 1.5 meters. Find the pressure on the bottom of the pool and then the total fluid force on the bottom of the pool. So first of all, pressure. Since we're working with, we're working with international units, so I'm going to have to go and say that I would know, hang on one quick second here, I would have to go with rho GH. And so I'm going to say, let's see, this is meters, so I'm going to say my rho is 1,000 kilograms per cubic meter. G would be 9.8, and H, this is the bottom of the pool, so the whole thing has a depth of 1.5. So the pressure, if I just multiply this out, gives me 14,700. And let's see, pressure here would be the international system, so that would be newtons per square meter. I stopped writing my units. I probably shouldn't have. This was 9.8 meters per second squared, right? And the 1.5 was the height in meters. So notice the 2 meters here cancel out 2 of those, and that's why I ended up with just meters down here, but then I changed that into newtons, which got rid of the other meters as well. So I end up with newtons per square meter. All right, total fluid force on the bottom of the pool. Force is pressure times area. We've already calculated the pressure, so we can use that. Our pressure, 14,700, times the area of the bottom of the pool. Bottom of this pool was 8 by 12. So length times width, 8 times 12. And I end up with 1,411,200. And the force would just be in newtons. The square meters here, remember this is meters and that's meters, would cancel out the square meters there. All right, so this is a fairly straightforward, just really an arithmetic process, as long as I've got a constant height. The bottom of that pool is all at the same depth of water. What happens, though, when I've got a plate that's not horizontal, all at the same depth, but rather vertical? So the different parts of the plate are at different depths. Let's take a look at that next. So this time, I'd like to find the fluid force on the sides of the pool. Because the surfaces are vertical, pressure against it will be at different depths. And I can't just use this algebraic equation anymore. I'm going to have to do it using calculus. Let's visualize what's going on here. I had this pool. And let's see, it was 12 meters by 8 meters. And the depth of the water was 1.5 meters. My goal right now is to figure out what the fluid force is, not on the bottom, we already did that, but on the sides. Now the front and back are both the same size, and of course the left and right are the same size, so I could go ahead and just do two calculations. One will refer to front and back, and let's do that one first. For the front and back, I've got this vertical wall that's 12 meters across and 1.5 meters high. I'm now going to go ahead and, very much like we've been doing, I'm going to say, let's imagine for ourselves a horizontal band or strip that's all at the same height or same depth of water. I'm drawing a little horizontal band here. And I'm going to say, let's calculate the force just on that one little horizontal band. So force on that little small band. It is going to be WHA, or I guess in this case again, rho G, HA. So I'm going to go back to rho, was that 1,000 kilograms per cubic meter, times G, 9.8 meters per second squared. And now I'm going to need to start doing some labeling. I typically like to let my variable equal 0 at the bottom of my plate. I'm going to use y this time. So we'll call that y equals 0. And the top here would be y equals 1.5. So if this strip is at a height y, then the depth, the amount of water above it, would be 1.5 minus y. So that's what I'm going to use for the h. H is actually the depth of the water. How much water is sitting above that little strip. And then finally, the area of the strip. Well, let's see, we've seen this a lot of times, right? I probably want to go ahead and say that little side here, let's call that delta y. So a length of 12 times a width, delta y, will be my area. So there it is, rho GH times the area of just that little thin strip. Of course, I now want to say I have a whole bunch of these little thin strips, and I'd have to add up all of the forces, or in other words, integrate. So the total force would be the integral of this. I'm going to call this 9800 times 1.5 minus y times 12 dy. And that's going to go from the y equals 0, would be the strip at the very bottom, to y equals 1.5, would be a strip at the very top. And again, not a difficult integral, but just for speed, I punched that into my calculator, and I got 132,300 international units, so this would be meters. We can analyze the left and the right sides in essentially the same way. Not that much is really going to change. The left and right would be 8 meters long, but still 1.5 meters high. And so if I once again imagine just a little thin strip that's all at the same depth of water. Here's y equals 0. Here's y equals 1.5. Then once again, if this little strip is y units from the floor, then the depth of the water above it would be 1.5 minus y. And the force on that little tiny band, rho g times HA, would be my mass density, 1,000, gravitational acceleration, 9.8, height of depth of the water above it, 1.5 minus y, and here's the only thing that's different compared to up here, this area. The area of this little strip this time would be 8 times delta y. Other than that, there wasn't much difference between these two problems. All right, to get the total force, then of course I'm going to integrate again from 0 to 1.5. And let's see, that would be 9,800 times 1.5, minus y. Times 8 dy. And again, I just went ahead and plugged that in my calculator. And this time I got 88,200 newtons. Makes sense, there's less fluid force on the smaller wall than there was on the larger wall. All right, this technique, and this is kind of what it says at the bottom of the page, but this technique is essentially what we're going to do. We're going to define a coordinate system. By the way, it's really common to use different coordinate systems. I typically like to let y equals 0 be the bottom, and then my y-axis is positive going up. You will also sometimes see these problems done with the y equals 0 at the top, and the positive y-axis going down. It's just a matter of a change in perspective. The answer will come out the same. So I mentioned that down here, but again, my personal preference is I usually do it this way, unless I have a really good reason not to. We'll want to find an expression for the area of a typical narrow horizontal strip, expression for the depth of that strip, and then we go ahead and plug into our force equation, pressure times area, or weight density times the depth times the area, or mass density times gravitational constant, HA. We then integrate to get the total fluid force. All right, I'm actually going to skip example 2 because it's just another problem exactly like the one we just did, right? It's an aquarium rather than a pool, but other than that, it's exactly identical. So rather than taking the time to do that, let's look at examples 3 and 4, which are a bit different. We have a non-rectangular plate being submerged in water. Or actually, this one's in concrete. This figure is the vertical side of a form for poured concrete that weighs 140.7 pounds per cubic foot. Notice that's pounds per cubic foot. So this time I was given the weight density of the water. The plate here is a triangle, and so I would like to go ahead and determine the force, the total force, on this part of the concrete form. So let's go ahead and draw in a typical little horizontal band. And I'm going to go ahead and define my variables. I'm going to let y equals 0 be the bottom here. And since this triangle is 3 feet tall, the top would be y equal 3. And that means that if this is at a height of y, then the depth or the amount of concrete that's above that strip would be 3 minus y. So right away, h, the depth, is 3 minus y. Area, the area of that rectangular strip is the length times the width. But here's what's different about this problem compared to the last one. Last time when we had a rectangular shape, all of the horizontal strips had the same length. That's not true for this triangle, right? Depending on where I draw, the length is going to be different. So I'm going to have to come up with a way to express that length in terms of y. We'll go with delta y. For the width, that's no big deal. And then I'm just going to use similar triangles to get the length. I'm going to say that if I call this L, the length of the rectangle, this height here is y, then L over y is equal to 5 over 3. So L would just be 5/3 y. So area is going to be L, 5/3 y, times W, delta y. All right, I think I've got everything I need. The force then on that thin band is weight density times depth times area. They gave us the weight density, 100.70 pounds per cubic foot. The depth for my picture over here, or actually I already wrote it down, was 3 minus y. And the area of that little strip, 5/3 y, delta y. In order to find the total force on this entire concrete form, I would integrate that. I could have pulled some constants out of the integral, I just didn't bother this time. And let's see, we're going from a 0 to a 3 up here for our integral. All right, again, just for simplicity, if you put that in a calculator, I got 1055.25, and that would be force in pounds for this problem. You can imagine these are the kind of things that are important to know because you need to know if your structure, whether it's the wall of your swimming pool or the concrete form, is strong enough to withstand that hydrostatic pressure. All right, one more. This one wasn't too bad. I just want to show you that depending on the shape, these can get a bit more complicated. So this last one, buckle your seatbelts. We're going to have a bit of geometry to do on this one. I'd like to find the fluid force on the vertical side of this tank where the dimensions are given in the problem. So my tank is this diamond-shaped window. It's submerged to a depth of 1 foot right here at the point, And then the window itself is a square that's 3 meters, I guess, on each side. All right, I'm going to do as I've done before. I'm going to define y equals 0, where the bottom of my plate is lying. And then this is where some of my geometry comes in. There's actually going to be quite a bit of it here. I need to figure out how to label the rest of this. So for example, I would need to know what is the depth here at the very top of the plate. Well, I can definitely figure that out with geometry. I'm going to draw in the horizontal line and then actually this vertical one as well. Probably need both of them. And let's see, what have I got here? Pythagorean theorem for this one. 3 squared plus 3 squared equals c squared. So 9 and 9 would be 18. And c is the square root of 18, or 3 square root 2. If this whole thing is 3 square root 2, then by symmetry, this is 1.5 square root 2, and this down here would also be 1.5 square root 2. 3 square root 2 goes all the way across, right? All right. That means that the total 3 square root 2 is the y value here. And then if I go all the way to the top 1 more meter, this y value would be 3 square root 2 plus 1. All right, I think I've got everything kind of labeled for myself now. Let's start figuring out our force. Okay. I'm going to have to do this in 2 pieces. I'm going to have to deal with the bottom triangle and the top triangle because the geometry will be slightly different for both of them. So let's start with the bottom. Oops, let's start with the bottom. If I draw a rectangle going across here, delta y would be the width. I'm just going to say L is the length. Then, once again, by similar triangles, I could compare this large triangle to this small triangle. So right now I'm working with the bottom. I could write that, let's see here, this is a height y, so L over y would be 3 square root 2 over 1.5 square root 2, which simplifies to just a half. Excuse me, no it doesn't. It simplifies to 2 over 1. So L would be 2y. All right, we'll use that to set things up here. F equals, in this case for international systems, so I'm going to go with rho g for my weight density, mass times acceleration, times the depth, times the area, and this is going to be just for that little band. So once again, we've seen it before, it's just going to turn out to be 9,800 when I multiply that, right? All right, what about the height? Well, let's see, that's actually the depth of water. What I have here is almost all the water is above that little band, right? It's the full 3 square root 2 plus 1 minus just this little y value that's underneath here. So that's the height. And then the area, length times width. The length was 2y. And the width is the delta y. All right, so hopefully that's everything I need. I think we're good here. That means that the total force on just the bottom I can get by integrating, and if you do want to pull out like the 9,800, you certainly can. Now my plate goes from y equals 0 to y equals 3 square root 2. Oh, excuse me. I'm only doing the bottom. So I'm going to use 1.5 square root 2 here, not 3 square root 2. And then we'll put this in. We would have 3 square root 2 plus 1 minus y times 2y dy. Looks kind of ugly, but if you throw it all in the calculator, comes out to 168,833.64, and we're in international units, so that would be in newtons. All right, let's see what has to change to do the top half. What's going to change here is actually this geometry of the similar triangles. If I look at that top half, and once again, I'm going to draw a little representative band across here, and say that's got some length L. This time, instead of having L being compared to that little tiny y, I have to compare L to this little bit of height up here. And that will equal the length 3 square root 2 compared to 1.5 square root 2. So how big is that little height right there? Well, let's see here. What would that be? We'd have this is 3 square root 2 minus, this is the y value, the height of this new strip. So it would be 3 square root 2 minus all of that y. It's going to be this little height. So let's put that in. L over 3 square root 2 minus y would equal 3 square root 2 over 1.5 square root 2. Just comparing base to height and base to height. That simplifies to 2 again, and then if I multiply this over, L would be 2 times 3 square root 2 minus y. All right, so the force on the little narrow band, rho g, HA. Again, we've seen it so many times. Rho g is 9,800 again. The depth. Well, the depth is going to be the same, isn't it? It's still the full 3 square root 2 plus 1 minus the y value, minus the height that we're already at, is going to give us the height or the depth of the water that's still there. So that's not going to change. And then this time my area, length times width. Length is this. And the width is delta y. All right. So we're almost there. I warned you this one was going to get a little more complicated with the geometry, right? The total electrostatic force on the top half, I would integrate all of this. And the top of the plate goes from 1.5 square root 2 to 3 square root 2. All right, and let's see here. I thought I did this one. Yes, there it is. I got 106, 466.82. Notice, by the way, that the electric static force on the fluid force on the top half is smaller than the hydrostatic force on the bottom half. Why would that be? Well, because it's not as deep, right? Less pressure exerted by this water because the depth was not as great for the top half as it was for the bottom half. If I want then the total electrostatic force, I would just keep saying electrostatic, hydrostatic force. If I want the total hydrostatic force, I will simply add the two values. And when I did that, I got a little over 275,000. 275,300.45. And again, this was all in newtons for our force. All right, that brings us finally to the end of this endless section, 6.7.